Welcome, everyone. Today's session will be on the co-design process for scientists and project leads, led by John Dennis of the Application Scalability and Performance Group at CISL. So, John, why don't you go ahead and take it away?
All right. Well, thank you for this opportunity to speak. Again, this is the co-design process for scientists and project leads. And how do I move my slides forward? Okay. Another title that I could have used, because I think it really addresses what we're going to be doing here, is should I be interested in GPU enabling my science? So what do we mean by co-design? Well, this is designing projects based upon hardware characteristics, software constraints, and science objectives. And so really what science, we're trying to ask the question, what science could GPU enablement really advance? And the thing to know, to keep in mind is that some science objectives are very well suited or GPU friendly. And unfortunately, other science objectives are not particularly well GPU, or not particularly well, very GPU friendly. That's not saying that, that science is any better or worse. It's just they don't have characteristics that make them, GPU friendly. So this is not, let's do GPU programming because everybody else is doing it. This is really trying to look at how we can advance science. And I wanted to, this is a warning here. This is 5 to 10 minutes from now, we're going to be doing some back of the envelope calculations. And so I wanted you to be ready for that. If you don't have kind of numbers associated with your science kind of handy, then go ahead and do that while you keep listening to the talk. So there's been multiple successful Earth system applications that have been GPU enabled. And here's a list of some fast eddy, large eddy simulations, MIRAM, which is a multidimensional magnetohydrodynamic code. CM1, which is a mesoscale atmosphere model. MPAS-A, which is the atmospheric component of MPAS. Samurai, this was a variational data simulation for an observational system that will hopefully in the very near future be flying on through storms. And also Home++, which is a spectrum and dynamical core used by the E3SM project. So a lot of efforts, successful projects. They have been by a number of different individuals. There's been some overlap, but a lot of this has been unique work. So we have some. Because we have a number of these projects, we can look at some of the common features and to go through them. So one of the common features is that they have a compatible science objective. And this was really identified. And the way you identify a common science objective with these projects was that there was somebody that was very familiar with GPU programming or GPU capabilities. There was also somebody that was familiar with the science, and they were able to say, oh yeah, that's a good fit. But the thing to realize is, or that we realized is that not everybody has this kind of crossover knowledge. And so the idea of this talk is to teach some of this crossover knowledge so that an individual scientist who, is not an expert in GPU architecture could actually say, oh, my science objectives could be advanced. So, but anyway, so this is about the, another feature of these projects is that the knowledgeable interdisciplinary team, you have to have domain scientists, you have to have, mathematicians, software people, and people that understand kind of the hardware. And so they typically have the design, they have kind of a very specific project design and knowledge about how to perform the transformations, code transformations that are necessary. It also had clearly defined achievable goals. So it was and significant stakeholder engagement and software engineering investments as well. So, you know, how to program OpenACC or OpenMP offload or CUDA. This is really other workshop sessions. So this is kind of and we're not going to go into that. We're just going to say, hopefully you reviewed that, or if this kind of inspires you, then that's probably someplace that you need to go and look later if you haven't done that already. What we want to concentrate is how do we identify when a science objective is a good fit, and kind of what some of the project design for the GPU enablement looks like. And so that's the target of this presentation. So here's an outline. So we're first, you know, discuss the motivation. We want to identify identify GPU-friendly science objectives. Then we're going to be looking at estimating the effort for GPU enablement and estimating the return on investment. So what do you really get out of it? So one of the things that we've done recently within the last year is we've gone around and we talked to a number of scientists throughout NCAR and talked to them about, like, what kind of science would you love to do, or what kind of science are you doing? And, you know, kind of got into some specifics. And so based upon these kind of discussions, you know, we kind of learned what we thought would be GPU friendly versus not GPU friendly. And so we came up with this list. This is certainly not exhaustive. This is kind of using a lot of intuition to place them here. So, you know, unlikely to be GPU friendly is probably paleoclimate and climate change. We'll go into specifics of why we think that is. Then there's the likely category: climate variability, ocean modeling process studies, high resolution whole atmosphere modeling with data assimilation, reanalysis, and then very GPU friendly. This is an easy, you know, this is a pretty easy list to create. Some of these already have applications that have been that exist today or are ready to run here in the next 6 months. So what you see here is that there's actually a good deal of relevant to NCAR scientific mission in the community that is likely or is GPU friendly. But again, there's some that are not. We'll go into specifics on how we made this assessment so that, you know, you can look at your science objectives and say, and kind of do a similar evaluation. So how do you determine if your science is GPU friendly? And this is kind of a fundamental question. Is it computationally demanding, and why? And so we came up with, so there's 3 kind of scientific simulations that we think are very GPU friendly. And one of them, and so we put some numbers here. And this is, again, you know, I'm going to ask you to pull out some numbers for your own codes here in a minute. So MPAS-A, this is an atmosphere, or this is a weathering model. So looking at very high resolution, 3.75 kilometer, very large number of grid points. The number of independent grid points is, you know, about 2 billion. And so the intended run when the derecho system gets deployed here in the winter time is probably about 300 GPUs per run, and the number of grid points per GPU is probably about 7 million. Now, you know, independent grid points. This is back of the envelope calculation. You can, you know, when you do this, I don't want you to get kind of hung up on, well, I have a K-level dependency or something like that, or I have a nearest neighbor dependency. I want you to kind of think of, you know, that's a lot of details. I want to keep it kind of a high level, again, an estimate based upon back of the envelope. And then there's like 1.2 million time steps. A CM1 simulation, again, this is an idealized mesosphere model. It has about 4 billion independent grid points. We intend to use 128 GPUs, about 33 million grid points, independent grid points per GPU. So similar order of magnitude, a little bit larger than the MPAS example. MURAM, also another large simulation. This has, in the total simulation, 9 billion independent grid points, and then per problem size per GPU, like 38 million. So, and these are all, so these are very large problems. And so these are all really GPU friendly configurations. And they're computationally demanding because of the number of independent grid points. All right, so that's the key thing to kind of think about when you're thinking about your own science. You could ask another question. What about a 1 degree climate change? And so, much smaller number of independent grid points. Again, we're kind of generalizing here. 1.7 million independent grid points. These are typically run on maybe 32 to 64 nodes. So that's about 27,000 grid points per node. Again, when we're thinking about GPU versus CPU, I always think about a single GPU versus a node. But you need to run this for 17 million time steps. And so the reason this problem is computationally demanding is because it's the number of time steps. The number of grid points is actually pretty modest. If you only had to run it like 1,000 time steps, then this wouldn't be a computationally challenging problem at all, I would argue. But very long time simulations. So there's other issues that I'm going to get into in the next slide. So another question is, does it perform a large amount of calculations between the I/O? For example, this might be a post-processing paradigm where you read in a variable, a three-dimensional variable, and you perform a sum on it to figure out what the average is. Efficient use of GPU minimizes the off-device transfers. And if you're going to be pulling these in from this subsystem, they're typically not a good match. All right. The other things to consider here is, does the science have a rate or a throughput limitations? So rate limitations means that you do need to run at a particular rate. So in that case, execution, on GPU should match or exceed the CPU rate. That would make it GPU friendly. An example of this is operational weather forecasting. You really do need to get the forecast out before the weather happens. So there's a really strict rate constraint on that. Long climate simulations also have this. You need to collect hundreds or maybe even 1,000 years of simulation together, and you need to be able to do this in a reasonable, quick amount of time. And so if it falls below a rate, then particular rate that people can set, then it can be problematic and it becomes unrealistic to run. So the other question, you could not have a rate limitation, but rather a throughput limitation. And this is, can you, and the question then is, can you do more science quicker or use less hardware? Some examples of these is maybe large eddy simulation, large ensemble climate modeling, seasonal to sub-seasonal forecasting. So again, we're taking the same model and we're running it for shorter amount of time steps, and we're potentially parallel. There's multiple ensembles that you want to have. So it kind of changes the characteristic or magnetohydrodynamics. So these are more throughput limited kind of science. All right, so this is your exercise. So pull out your envelopes or whatever scrap of paper you have. And I would like you to determine the following: the total number of, and when you do this calculation, I would encourage you to think about what you're doing today and what you might want to do in 5 years or in the near future. So, think about the total number of independence grid points that you have. Again, let's gloss over the K dependence or the nearest neighbor dependence. The number of nodes or GPUs you run on per run. I'm assuming it's more likely nodes for this audience. Then the number of grid points per device, and then the time step, number of time steps per run. And so then you ask the question, does it perform I/O frequently? And do you have rate or throughput limitations? And I want you to go ahead and do that for the next 5 minutes, and then hopefully you'll share out some interesting realizations that you may have had. And if you have any questions, you can always ask it in the chat. All right. Well, so I hope we have some information that you'd like to share, like realizing that GPU might be, your science might be friendly. Does anybody want to share? I do know some of you on the call, so I could call on you specifically.
Go ahead, Frank.
Yeah, John, you probably know what I'm looking at, but I did have a question about how, in terms of not just number of grid points, but how many degrees of freedom you're carrying at each grid point, whether, so for example, if I was doing an ocean simulation and I was carrying a dozen tracers along with the standard prognostic variables, would that effectively, would you consider that an increase in compute intensity as if you were just increasing the number of grid points by a factor of 12, or what? How would you factor that in?
Well, okay, so this is where it starts to get a little bit beyond back of the envelope calculation. That's going to that's going to undoubtedly increase the cost of a certain section of your code by a factor of 12 or something similar like that. So, but you know, what we're trying to get at here is just kind of a general sense of how big the problem is. So I would say that the tracers don't count as independent grid points for at least the rough estimate. You know, so that's my thought.
Okay.
Go ahead, Naoki.
Hi. Just yes. Yeah. So I have a Riva model running in a global, and eventually trying to run a very high resolution, which is about 10 million Riva segments, and then that's probably, you can say, like a independent grid point. And then, as Frank said, it's very dependent each grid points actually. So I'm not sure that this works, but so right now, testing like CPU 40 nodes, so like 1,200 cores, which is probably like I don't know how many grid point per. Is it talking about nodes or a core?
Yeah, I would focus on nodes, because a node should be compared to a GPU. I think that's the fairest comparison.
Okay, so it's like only 40 nodes.
It's and you said
So
10 million.
yeah, for now it's like a maximum 3 million, but there's a data set I see like about 10 millions in the global, which I'm not sure we end up in using this in the future, but a maximum I see is 10 million right now.
And do you have a rate or a throughput limitation?
So that's my question. I don't. So it's a kind of naive question. What's the rate and throughput? And
Well, so a rate limitation would be you would be doing maybe numerical weather forecasting, and you want to do a 5-day simulation, and you want it to be able to produce it every 3 hours or something like that. So if you miss your 3-hour window, then you're kind of, it's a problem, right? But a throughput limitation would be like, I just want the results, and I want to be able to, look at them and publish a paper on it. And, so it's kind of the length of the run is really dependent here.
okay, so let's say this is a climate change application. So like well, some people use like seasonal forecast, but I don't think using for global. So and I don't think it's IO frequency is about daily, or depending. This is also depending on application, climate change application, maybe daily, but that could be monthly too.
Yeah. Well, so I mean, where this comes into, I'm trying to make this general. So if you're doing post-processing analysis that, that reads in data and calculates, the average on an array, then that's kind of high frequency IO. If you get on a system and you run for, you do a number of calculations, which it sounds like you do, then that's not IO limited. So, or it's less IO, less risk of being IO limited. Okay, so climate change, how long are you wanting to run this? Is this hundreds of years?
Hundreds of years, I think.
Yeah. This sounds like a climate kind of change, kind of like problem.
Yeah, I don't expect this is a GPU friendly. Is that right?
That's my 2-minute assessment as well.
So like, I don't think Riva will never go beyond probably 10 million. So good point, probably much less than what you talk about, like other models. So
Yeah.
okay, that's okay. I'm sorry, I don't wanna
No problem.
dominate. So thank you very much.
Is there another example that we might want to discuss? We only have a couple minutes left here.
Supreet raises his hand.
Yes, Preet?
Oh, well, if we don't have any other application, then I just want to ask a couple of questions about the previous application.
Okay.
Or we can have
We
a,
might need to move on. Can we have those questions for after the session is done?
yeah, absolutely, yeah.
Thanks.
All right, so there's no more different applications that people want to share. Is that my? Okay. All right. Let's move on then. So the next step comes to estimating the effort to achieve GPU enablement. And this is a little less numeric because I think it's more challenging, and it's not a matter of kind of adding up or multiplying out a bunch of numbers. So the first question that you have to ask yourself is, a GPU enabled version of your code, does it already exist? And this is great. Because then the effort to actually do your science, use GPUs for your science is pretty simple. Or it can be very simple. The one potential challenge here is the version of the code support all the necessary physics options? And so that's a consideration. For example, if you may want to use MPass-A and your favorite parameterization is not GPU enabled, in which case it becomes more difficult. The other things to consider is it's really to ask the question, is the code written in such a way that is GPU ready? And what do we mean by this? There's really three kind of conditions here. Is there a significant or a full amount of parallelism that's available at the loop level? Does a threaded, for example, OpenMP version of the code already exist? And does the code have some form of verification for correctness? And we can say a little bit more about what these three conditions are. So the first one is significant parallelism available at the loop level? Because the reason why we want to think about this is needing to rewrite the call structure to support significant parallelism can be very time consuming. And so here's provided an example of a GPU ready loop arrangement. This was pulled out of CM1. So this is a triply nested loop that updates whatever W10 is using several other variables. So this is very, basically all the parallelism is right there exposed in this loop. Loops that are in need of rearrangement, and this is a kind of an example that we made up, but you see it commonly in various different codes, is where there will be the parallelism is kind of strewn throughout. So in this case, you call the radiation solver 2024 times, and within the radiation solver, you call it on a piece. You call LW solve 128 times, and then at the bottom of you perform some long wave solve over 256 points. So what you see here is that in the first example of the loop, full parallelism is available at the loop level. It's just right there. But the problem is with the second example is that limited parallelism exists at the loop level. So you really only have 256 wave parallelism at the LW solve kind of level. And so, scientifically, you may have the product of 1024 by 128 by 256, but the way your code is written in particular, you really only have 256 wave parallelism at the loop level. So typically what we have to do is we have to rewrite it and push the parallelism down into the loop level. Another important consideration is, does a threaded version of the code already exist? And this is important because OpenACC and OpenNP offload constructs, and honestly CUDA is technology are very similar to existing CPU-based threading from a broad conceptual perspective. There's a lot of details that you have to sort out and keep straight. So existing threaded versions indicate that parallel issues have already been considered and thought about, and so that's a good thing, and that can save a lot of time. The thing that is still relevant here is that existing threading approaches may need to be reworked. Daniel, I have a question. Did we restart the recording?
It's still recording. You're good.
Okay, thank you. And because the reworking of the threading approach, GPUs need a much larger level of concurrency. And does the code provide verification? Code verification is very useful because it allows you to do incremental GPU enablement. Much easier to retain correctness than to regain correctness. One of my personal experiences is that addressing correctness bugs typically take the majority of the code conversion time, and it really simplifies the time of debugging GPU-enabled code. And and I think I want to comment here, verification kind of at the hopefully it's easy to do, right? The verification, having to run a code. Having to run a code for 12 hours and then looking at plots can make the debug cycle very long, because it's like 12, every time you make a change, it's 12 hours. So hopefully the verification occurs at kind of a small and granular level so that you can have your debug cycle be kind of quick. All right, so this is another student exercise, and I hope I'm going to pick on other people maybe. So is your code GPU ready? And so I kind of made this up. There was a series of questions. I'm going to give points for yes or points for a no, and then you add up all the points, and the larger the number of points, your point total, the more difficult it's going to be. So I'd love to say that the points correspond to agile story points and that you can, translate that into FTE months, but they don't. But this exercise is kind of a, how much effort is it going to be? So, I mean, if you have a code that has 3 points of difficulty, that's going to be a lot easier than if you have a code that's 25 points of difficulty. And so Again, coming back to the CM1 example, so we filled this out. So is the GPU version of your code already existed? That's a no. So that I got 4 points for that. Is the code written in such a way that it's GPU ready? Thankfully, yes. Does a threaded version of the code exist? Yes. And does the code have some form of verification? 7. So it didn't. So we needed to create that, and we actually moved forward before we had a solid form of verification. So that was challenging. The point score for CM1 was 13. It could have been much worse, like 25, or it could have had a verification suite, in which case it would have been 7. Anyway, so I wanted to give you some time to think about this, to see if your code is GPU ready. Hopefully, we'll have more discussion from the audience with this. All right. So, anybody have some point totals that you'd like to share? If not, I'll pick on people that I know. All right. Frank Bryan says mom 6 is an 18.
I'm guessing you've already done that evaluation, John. What would you say?
I haven't actually looked at mom 6, honestly. So that's so yeah.
So I go through it. I mean, there is not currently a complete GPU implementation. I know that folks in your group have worked on small components of it.
Yeah.
I think there's a lot of loop level parallelism in there, but it's not pervasive.
Mm-hmm.
So I give that a 4. There is some limited threading, but we are not typically using that right now. So it's not as well tested as I would want before I gave a smaller number. So I give it a 6 there. And it does have some built-in verification, at least dimensional consistency testing. This is kind of a cool testing thing that Bob Hallbriggs developed. And, we can do exact restarting, that kind of thing. But if we're going outside bit for bit, then the ocean model has not had as much success with doing the kind of per-limb solution divergence testing as the atmosphere has done in the past. So,
okay.
So anyway, I came up with a total of 18.
Cool, thank you. I was wondering how you got a number that was not additions of 1 and 4, 7. All right, anybody else that would like to share?
I have a question I could ask Frank. So does having a high point total there for mom 6 concern you with respect to like investments you might need to make in your team to make a GPU version of mom 6 feasible? Or does that concern you and say like push you away from even making further efforts towards GPUizing mom 6?
Well, I guess I'm somewhat discouraged, but I think that the larger concern for us is that this is a model that's used across agencies, and that that's very important to us. So we are reluctant to just go and take off on our own and create a version of the model that runs very well on GPUs, but is unsuited to use by our partner institutions. So that, I think, may be a larger concern than the effort required. I mean, if we have buy-in from the other institutions, then I think it becomes a less daunting task to do this kind of work, because we can potentially share it across, NOAA, NCEP, GFDL, and ourselves.
So I wanted to respond to that. You know, I pointed out kind of the applications that have been GPU enabled. All but one of those are CPU GPU codes. And the choices were made to basically do GPU enablement and not have a major impact on the CPU capability.
Yeah, I think the concern is more that, you know, this is a research code that is constantly under development with new parameterizations and new algorithmic advancements. And, you know, we want to maintain that accessibility of the code.
Yeah.
So recoding in a way that makes it more difficult for our partners or university partners to contribute to improving the physics in the code is something that is we'd like to avoid.
Yeah. All right. Well, I think that's further discussion. I wanted to see if anybody else would share their point total. Maybe Allison Baker would like to share her point total.
I don't have a point total to share.
Okay.
I'm just following along.
All right. Any other scientists that would like to, or project leads or other people, I guess I shouldn't discriminate there. Any other people that would like to share point totals that they came up with?
I have a question though,
Okay.
if no one else has anything to share, since you called on me.
Yeah.
Are we pretty much thinking about Fortran and C and C++ codes? I mean, sometimes, you know, using Python, you do get something that obviously doesn't have a billion unknowns, but is very challenging for what you're trying to run and could possibly benefit from a GPU through Python. Are we not really talking about that today?
I think Python codes are viable, right? I mean, this comes down to the mechanics, which is the thing that I said in the beginning of the talk, see other sessions, right? So, I mean, I think, you know, what we're trying to get a feel for here is, you know, how big the problem is, what kind of IO characteristic it has, and do you need to do 1 million time steps, or, you know, do you need to do a small amount of time steps over a billion, right, unknowns, right? But, you know, the analysis code can be appropriate for this as well. Does that answer your question?
Yes, thank you.
Okay.
I was thinking about analysis codes, which can often take much longer than you'd like them to.
Yes. All right. I'm looking for one more person to share before we move on. All right.
I can add one point, John.
Yeah.
So I think if you go a couple of slides up, you gave an example about the loop structuring.
Yeah.
I think it was a pretty good example. And also I'd add just one point to that. So when we talk about the codes or the code structure, which is not kind of GPU friendly, it's not just about the calls inside. If your outer loop where we can extract the parallelism is at a much higher level, then it's a problem as well, because we cannot simply abstract the parallelism. We can just abstract the extract the parallelism at a higher level, but it actually doesn't extract it doesn't actually utilize the full extent potential of the GPU. So you might want to think restructuring your code in such a way that your loops are closer to your K loops as much as possible.
Yes, yeah. No, absolutely. We're trying to get a rough estimate of how much restructuring needs to be done. So, all right, so I'm getting a message that say, let's move on. All right. There'll be another opportunity for sharing. So estimated return on investment. And so what kind of capability will GPU enable deliver versus existing codes? And so I think a key thing to consider here is, are you know, what your base case is. So if you have a serial base case, then you could get really high speed ups. And this is, you know, this is when you hear NVIDIA promotional talks about getting 50x or 100x speed ups. That's because they're basing it off serial versions of the code. And that may be the case for some analysis codes, for example. But you know, when we're creating, you know, the examples that we saw at the beginning of this talk were codes that were you know, an efficient CPU implementation existed. So so some potential advantage to the creation of a CPU and GPU enabled code: reduce time to discovery for a particular science question, access broader collection of hardware. You know, there is quite a lot of non-CPU compute hardware out there, particularly at large scale at DOE laboratories. Ability to perform more science for a fixed resource cost. So think about shrinking the footprint that you need to run. And ability to perform science that would be not otherwise possible. And so this is, it's a really nice feature if that's the case. So the advantage of GPU computing is a result of better memory bandwidth and floating point rates. For derecho, this is again the system that NCAR will be installing in the early spring or winter. Anyway, so it's a NVIDIA A100 versus an AMD EPYC. That's the CPU component. What you see from a specs perspective is that there's about a 3x increase in memory bandwidth for the A100 and about a 1.9x increase in the theoretical floating point 32-bit or 64-bit rates. This is the thing to emphasize here is this is not using tensor calculations. This is kind of just the generic floating point rates. If you can use tensor calculations, then there's a much larger floating point increase possible. So, all right, so this is going back and looking at the loops. And so the way to kind of get a handle on this is, what is the working set size for a tightly nested loop? We're going to look back at the typical loop in CM1, the triply nested. And so if you do your math here, you got loop accesses for different variables. It happens to be using 4-byte reals, and the extent of them is the 128 by 256 by 1024. So you do the math, and the total data access is about 512 megabytes, and this happens to exceed the 256 megabyte L3 cache on the AMD EPYC. So what this means is that this loop is going to essentially be, having to pull data in from main memory. So this is going to be a memory bandwidth limited calculation. So you see about a 3.8x potential speed up. And a thing to note here is that when we looked at the overall CM1 speed up, we got right about that. We got a little bit better because we're using a smaller memory footprint, and so our message passing cost is smaller because we're, instead of using, because we can replace, 16 CPU nodes with one GPU based node. So we get a little bit better than the memory bandwidth speed up. So this is a student exercise. I hope they're gonna have sharing again. Maybe I'll pick on Frank again because he's been the brave one. So what's the estimated return on investment? So, again, what is your working set size for the inner loops? Hopefully you have this data and you can reuse it. So, if it's a memory bandwidth limited, then your return on investment may be about a 4x if it's more flop dominated. And so that's the maximum return on investment here. And I think the most critical thing, and this is something that I cannot comment on, obviously, is would this kind of return on investment have a meaningful impact on your science? And all right, Daniel says we've got 4 more minutes. So anybody would like to share? It's a quiet group. All right. Frank says he doesn't have the data for this one. All right. Anybody else that's been holding back would like to share?
Go ahead, Anne, you have your hand raised. You're still on mute, Anne.
Sorry. What's the impact of needing greater than 256 megabytes cache? How much does that cost you? Does that cost you twice as much, or what? Ballpark.
What do you mean by the cost? So I mean, it's going to be basically your program's going to be accessing main memory, which means that you're going to slow down significantly.
Well, how significantly?
You're going to be waiting for main memory access, which so if you were using a GPU, then it would run 4 times faster because you'd have 4 times the memory bandwidth.
4 times. Okay, thank you.
All right, I'm gonna move on and just say, here's my email. I'm happy to have further discussions with you. There's some additional resources about some co-design work that have been done in Europe. So comment on your own return for investment for GPU. Yeah, so again, anyway, so the code that I'm most familiar with, the CM1 had a factor of a clean factor of 4 improvement, and so basically there's going to be four GPUs per node, so it's going to use a factor of 16 less compute nodes on derecho, because we're using the GPUs versus the CPUs. MIRAM, I don't know what the exact MIRAM number is. It's probably a factor of 2 or 3. You see similars with MPAS-A, probably a factor of 3. Other people could comment on exactly if it's 3.3 or 2.9. All right, it looks like we're 1 minute over. 3.7 for impasse A. Thank you, Supreet. So yeah, so it's about, 3 to 4-ish.
We had one question from Frank, I think. He raised his hand again.
Oh, okay.
If we have time, this is a little bit in the weeds, but or specific. So I'm kind of looking at a newish code called Oceananigans, which is developed from scratch in Julia, and as a possible replacement for some of our Ocean LES work. And at least the advertisement is that the Julia sort of hides much of the complexity involved in getting performance out of the code on GPUs. I'm wondering if John could comment on that.
I know of the existence of Julia. I have not, our group has not had direct experience with it. So this is something that I sound like I would probably want to talk to you offline about.
Okay.
Yeah. All right.
Thanks, John.
Yeah, thank you.